Page 16, number 77. Identify if the triangles are similar. If similar, select the proof that justifies your answer and show your work. So there are only three ways of proving if triangles are similar. Now, one of the ways, very famous, SSS, the side-side-side similarity postulate, which is listed last over here. It checks that all three pairs of sides are in proportion. And when we think similarity, we think proportions, proportions, proportions. The second similarity theorem is SAS, which says that the two pairs of sides are in proportion, but the angle in between them is congruent. So angles should never, ever, ever be different sizes if you're looking at similar shapes. Lastly, the AA similarity theorem, which says if you have two pairs of angles congruent to two pairs of angles in another triangle, then the two triangles are similar. You don't even have to know that third pair of angles. That third pair of angles will automatically be congruent because of the third angles theorem. But let's go ahead and take a look at our options and see which theorem we're going to use to try and prove similar, and then are they similar. So for the first one here, notice I only have two pairs of sides between my two triangles. But what else I have is I have vertical angles at A. So I'm going to use the SAS similarity postulate to try and see if these two triangles are similar. Now I know for sure that the angles are congruent because they're vertical angles. So that part is good. Now let me check if the sides are in proportion. Before I do that, I have to match up the side lengths. So for the triangle on the left, I have 22, which is the longer side. Between 22 and 20, it's the longer side. So looking at the triangle on the right, I want to pick the longer side, which is 11. So 22 matches up with 11. The same way that 20, which is my shorter side, should match up with 10, which is the shorter side for the other triangle. Let's put these into fractions and see if they're in proportion, if we get the same fraction. So 22 over 11, and then we have 20 over 10. For 22 over 11, I can divide the top and bottom by 11. And when I do that, I get 2 over 1. For the right side, I can divide top and bottom by 10. And I get 2 over 1. Notice that both of these are the same ratio once I've simplified it. So if they are the same ratio, if they're equal, then these two sides are in proportion. So perfect. The S's are also proportional. So I use the SAS theorem, and the SAS theorem says that yes, they are similar triangles. Let's look at the next one. Now for the next one, I have two triangles that are overlapping. I have triangle YVZ, and then I have the larger triangle that's behind it, triangle WVX. Now I'm going to go ahead and erase that because what I want to do is I want to check if the two triangles are similar and I don't have any side lengths. Instead, I'm going to have to try and use the AA similarity postulate and see, do I at least have two pairs of angles that are congruent between the two triangles? Now, I do know that I have angle V, which is an angle that they share. Angle V is part of the small triangle and the big triangle. So that's definitely one pair of angles that they have congruent. So I'm going to go ahead and write out my AA similarity. So I definitely have one pair of angles congruent. Now for my second pair of angles, they didn't give me any measurements, but I do see that these two lines are parallel. So when I think parallel lines, I'm thinking the Zaro Z for alternate interior angles, but that's not really going to work here. So the next thing that I can look for are corresponding angles. So corresponding angles are the ones that are in matching positions. So if I look at the bottom side, VX for example, if VX is my transversal to those two parallel lines, then that means that I have angle Z and angle X congruent because they're corresponding angles. They're in matching positions. So that's my second pair of angles that are congruent. And just for fun, I want you to note that if I consider VW as my other transversal, then again, I'm going to have angle W congruent to angle Y because they're corresponding. They're in matching positions. So really, I have AAA, like I mentioned before, because of the third angles theorem, but really all you need is 2 pairs, and then that's enough information. So I'm going to say again, yes, these 2 triangles are similar because I have at least 2 pair of angles that are congruent between my 2 triangles. Last one. So look at the last one. Again, I only have angles. I don't have any side lengths. So I can't use SAS and I can't use SSS. That would require us to compare the sides and see if they're in proportion. Now, I do have 2 pair of angles on the left triangle, 61 and 49. For the triangle on the right, I have 53 and 61. Well, right now, I only have 1 pair of angles that are matching. So right now, using my AA similarity postulate, I only have 1 pair of angles. Now, I do have a pair of angles missing in both triangles. So I'm going to solve for the missing angle and see maybe that pair does match up. So I'm going to go ahead and I'm going to subtract 61 and 49 from 180, because we know all angles should add up to 180 in a triangle. I'm going to see what's left over for angle M. So in my calculator, 180 minus 61 minus 49. I have 70 degrees left over for angle M. Now 70 doesn't match up with 53. Now it's probably not going to match with angle F because my last angle is 49. But just because we want to be thorough, we're going to go ahead and figure out what angle F is as well. So same thing, take 180, subtract 53, subtract 61, see what you have left, which is 66. So at the end of the day, I only have 1 pair of angles that are congruent. I do not have the second pair. So I cannot say that these 2 triangles are similar. The answer is no, even though I tried to use AA similarity. It's just that the AA similarity postulate said no, they are not similar. You don't have enough information. Okay, let's move on. Number 79, write the sides in order from smallest to largest. Okay, let's take a look at this triangle in order to order from smallest to largest. Now they're asking us about side lengths. However, we don't have side lengths, we have angles. Now you need to know that the largest side is always across from the largest angle. So what we need to know first is what's the measure of all 3 angles in this triangle. So I'm going to go ahead and I'm going to figure out the missing angle, angle Z, so then I can think about what's largest, what's smallest, yada yada. So I'm going to say 180 minus 39 minus 46 and see what we're left with. Okay, 95. So we have 95 degrees left for angle Z. Now, I'm going to go ahead and zoom in on that triangle. Okay, now the largest angle is always across from the longest side. So our largest angle is the 95. So that means across from it is the longest side. So across is XY. So I'm going to go ahead and put that in, that my longest side is XY. Now, oh, that's in the wrong spot. I'm looking at my inequality symbol. So for my inequality symbol, I need to put the largest one all the way to the right. So x, y. That's my longest, my largest side. Okay, so let's go back. Let's see what our next side is going to be. So let's take a look at what our shortest side is going to be. Our shortest side should be across from our smallest angle. So looking at our three choices, 39 degrees is my smallest angle. So across from it is going to be my shortest side, YZ. So YZ is going to be the shortest side. Let's go ahead and put that into our range. Go ahead and put YZ for our shortest side. And now the last side length, well, the last side length is going to be across from the 46, so it's going to be XZ. So looking at our triangle, we have our 39 degrees, which is our smallest angle, across from our shortest side, YZ. Our medium angle is the 46 degrees, so that's across from our medium side, which is the XZ. And lastly, the 95 degrees, which is our largest angle, is across from our longest side, XY. Okay, let's move on. Number 80. Here's our word bank. Orthocenter, centroid, incenter, circumcenter, altitude, perpendicular bisector, angle bisector, median, and midsegment. So we have to fill in the blanks. A. The blank is formed by perpendicular bisectors. Okay, perpendicular bisectors, when drawn into a triangle, cross at a point known as the circumcenter. Circumcenter. B. Angle bisectors are concurrent, which means they cross, at a point called the blank. Okay, angle bisectors cross at something known as the incenter. C. The blank connects the midpoints of two sides of a triangle. The midpoint of two sides of a triangle, we're looking at midsegment. The midsegment connects midpoints of two sides of a triangle. So we're going to label in midsegment. And lastly, D. The blank is equidistant from each vertice of a triangle and is useful in finding a point equidistant from three locations. Okay, there is a really important concept here. If I have a point that I want that's going to be the same distance to all three vertices of my triangle, what I'm going to look for is a point known as the circumcenter, which in part A, we see the circumcenter is formed by perpendicular bisectors. So if I get the perpendicular bisector of each side, they're going to cross at a point known as a circumcenter. So again, for D, my answer is circumcenter. So this is a big vocab question. Okay, moving on to 81. Number 81. Find the perimeter of triangle KLM. Okay, so triangle right here in the center, right here. So to get perimeter, we have to add up all three side lengths that make up KLM. So I'm going to get started and set up a little bit of a graphic organizer. So P equals, we have three sides for the triangle. One of them is KL, which we already know, it's 7. Another side length is LM, and then the last side length is KM. Now, they have a lot of markings here about what's congruent. Let's take a look at the left-hand side here. I want you to note that K is the midpoint of the left side of the triangle because it's going to split the left side into two even parts here. On the right side, I have line segment HJ, and L is also the midpoint because it's splitting the right side into two equal parts. On the bottom, same thing. I have a midpoint, M, because it's splitting the bottom into 2 equal parts. This is forming 3 line segments that are connecting midpoints. What we have here are 3 different mid-segments. Mid-segments forming a mid-segment triangle. Now, one thing that you need to know about mid-segments, we'll focus in on one of them. Let's focus in on ML. Mid-segments are parallel to the base, so ML will be parallel to GH, and mid-segments are half the length of the base they're parallel to. So if my mid-segment is ML, and it's parallel to this length of 12, then I have half of that length as 6, and that's the length of my mid-segment. So half of 12 is 6, and that's going to be the length of ML. Now looking at the last mid-segment here, KM, because I already have the 7 for the one in the middle, KM will be parallel to HJ. And HJ needs to have some type of length so I can figure out what half of it is. Now notice I have 2 pieces here that are equal because I have 2 tick marks here, 2 tick marks here. So that means HL is 4. So the entire side length for the right from H to J is 8. So if KM, which is my mid-segment, is parallel to HJ, that means it's also half the length of HJ. So that means that KM is a length of 4. So now I know all 3 lengths for my mid-segment triangle. I'm going to go ahead and fill in my little graphic organizer. I'm going to put in that LM is 6 and that KM is 4. And I'm going to add all of those together. 7 plus 6 plus 4. 6 plus 4 is 10 plus 7, we're at 17. So my perimeter is 17 units. So this is an application of the mid-segment. So just put this note in, and you may want to put a little diagram on the back of your reference sheet. But when you have a mid-segment, that means it's connecting 2 midpoints. And it's going to be parallel to the base. And it's going to have half the measure of that base. So for example, if the mid-segment was X, the base would be 2 times that amount. So you would always double the length of your mid-segment times 2 to get the length of your base. Or if you work backwards and you have the length of the base, you would divide it by 2 to get the length of the mid-segment. Okay, well that completes page 16.